you wish to calculate. So that is algorithm, the way to implement that. Now, why are they even important? Can't we just write a plain set of programs without even considering the say like in technical terms it is called time complexity, and in general terms we can say the how much time program will take to process the information or to produce the output. That is known as time complexity. Let me show you. Okay, so it is known as time complexity. So as the name suggests, time complexity is somewhat related to time. Okay, so we know that our processor is like capable of doing up to a certain number of processes only in a given second. You all might be knowing that the processors are like the frequency is calculated in gigahertz. So what is gigahertz? It is 10 power 9 instruction per second. Okay, instructions per second. So let's say we can calculate the sum of 1 to 10 power 9 in a given second, even though like these are not simple operations, but let's say we assume that we can calculate these many integers. Okay. Now, you might be familiar with prime numbers. Uh, like in Hindi, it is called abhajya sankhyaएं. Okay, prime numbers. So in Hindi it is called अभाज्य संख्याएं. So जैसे नाम बता रहा है अभाज्य संख्या means like which do not have any what is it divisors except one and the number itself. Let's say any number n, it is prime only when it is divisible by 1 comma n only. No other integer exists between 0 2 to n minus 1 such that n divided by that particular say number x is a say integer number only. No such integer x exists. So then we say that the given number n was a prime number. Now, like we all have studied this in our schools and maybe in colleges also. Now, what is the procedure to check if a number is prime? Check if a number is prime. Okay, number is prime. So to checking what we can do, we can just check for every number in the range of 2 to like 2, 3, 4, 5 up to n minus 1. Whether n is divisible by any of these numbers, then we will say that, oh no, this number is not a prime number. Okay. And in case we do not find any number that divides n, so we will say that the number was indeed a prime. So that's the like most basic approach that one can think of. You can say if you are calculating, like if you are checking for a number ranging around 10 power 18, then what you need to do? You will iterate from to, you will just check, iterating means just checking from, okay. So you will just check for 2, then you will just check for 3, then 4, then 5. Like that, you will proceed until 10 power 18 minus 1. That is some 17 times 99. So that's a very big number. And just I mentioned here, like processor are like its frequency is measured in gigahertz. What does gigahertz means? 10 power 9 instruction per second. So how much second it will take? So we are doing 10 power 18 instructions, and in each second we can do 10 power 9 instructions. So it will take roughly 10 power 9 seconds. So like it might sound you a small number, but 10 power 9 seconds, it's a very big. You can say 10 power 9 seconds is nothing but something around 200 days. So like no one of us will wait for 200 days just to check whether a like given number was a prime or not. Like no one has that much patience. So what we will do, we will use a certain mathematical trick here. For any number you suppose, any number you take, we can say that divisors exist up to only root n. Like after that, divisors will start repeating. Let me show you an example. Say for example, take n equal to 100. So we say that root n is nothing but 10. Okay. Now, what are the divisors of 100? Indeed, like 1 is divisor, and it's say what to say that its complement, you can say like n by this number. So 100 is also a divisor. Then we will say that 2 is a divisor of 100, then 50 is also like 100 divided by 2. Then we will say that 4 is a divisor, then 25 also is a divisor, like 100 divided by 4. Then 520, and then comes, yeah, 10 comma 10. Now the next divisor are 25. Okay, let me write with this with a different color so to differentiate them easily. So what are the next divisors? It's 20 comma 5 is 25 comma 4, and it's 50 comma 2, and at last we have 100 comma 1. So we can certainly see that these numbers are repeated, uh, and this 10 by 10, it is exactly root, so we are not writing it twice. Otherwise we can say that these numbers are repeating only. So if we just check till root n only, will it work? Like we are just checking till root n, we need not to iterate from 2 to n minus 1. Instead we will just iterate from like iterating with looping only, like checking for every number in the range of 2 to root n. If we can just check within these possible integers, then we are good to go. Like there is a mathematical proof also, and you can also prove it by say contradiction or maybe some hypothesis. So now what we will do, like for that example only, we consider n equal to 10 power 18. Its root n is what? It is 10 power 9. So now we will just need to check in the range of 2 to 10 power 9. And as I said, like the processor can compute 10 power 9 instruction per second. So how much time will it take? 1 second. So you can say just using some mathematical trick that is nothing but a part of algorithm only, we can reduce our time from 200 days to 1 second. You can see like this is some god level improvement, like where it was taking around 200 days to compute something, now it is taking only 1 second to compute the same thing. So it is like very much powerful. Now like by using the same idea, you can say like given a number n, given number n, you need to find what all are the divisors of this number. Like let me just say, if I'm clear, please like give a thumbs up, or maybe you can just speak. Okay, I believe like there are no certain like difficulties in understanding the concept that I'm telling. Okay, so like given a number n, and we are interested in finding divisors, finding divisors of this number. What do divisors means? The number which divides the n like without leaving any remainder. For example, 10 is a divisor of say 20, 30, and all the multiples of 10, like that. So earlier what we used to do, like we will iterate from say 1 to n minus 1, and we will just check if any number is a divisor of that number. Now what we need to do with some algorithmic concepts, we can just iterate from 1 to root n, and we will just check for example, let's when looping through these elements, let's denote them with I. Okay, we will just check if n okay, this percentage is nothing but the remainder operation. Like when n is divided by I, what is the remainder? And if it is equal to 0, we will just say that okay, I divides I divides n, and also n divided by I also divide n, because that is pretty obvious. Because any number you take, say for example 200, and we say that 5 is a divisor of 200, then 200 divided by 5 is also a divisor, that is 40. Okay, for any number the same rule will apply except for the root n, because for root n, let's say if n is a perfect square, for example 100, then root n will be okay, just a minute, then root n will be 10, and n divided by root n will be what? Root n again. So we are just repeating the number, so we can just handle this case explicitly, and for all others number we can proceed using the same logic. So you see like how much improvement we are getting just by using say plain use of mathematics only. There are no advanced concepts involved, at least till now, even though there are some advanced concepts in the algorithmic field where we have certain data structures to compute the things. But in general purpose, we do not find those like very much say useful in our daily life. Those are required obviously, but at a very like complex level. Okay, so we can say that with only high school level mathematics, or even below than that, we can say make our system very much powerful. Like no matter how much fast CPU you have, for example, you are like buying a latest CPU, but you can't perform say exponential number of operation in that. It will anyways take time, no matter how much the technology will succeed. You will always make the software efficient so that it works on like a lower grade processor also, and on a higher grade processor it works like more than more fast. So we have seen this example. Now let me give you another example showing the importance of algorithm. Say another example. So in this example, what you have been given? You have been given some list of elements, like list of integers. So for example, x1, x2, x3 up till xn you have been given, and now I gave you a number capital X. Okay, and I ask you search that whether capital X is in this list or not. So the people, what they will do at the prime phase is they will just check for like compare X with every element in the given list. They will firstly come like compare this with x1, then they will compare with x2, and until xn. So we can say like you will like given n is the size of list or number of elements present in list. Anyways, you take so okay, size of list, not size of elements. So size of list. So you will like waste n number of steps. N number of steps are to search required to search for given capital X. But do we need that many steps only? Like given that these elements are arranged in a proper order. By order here I means like either they are in arranged in an increasing order, either in increasing order, or in decreasing order. So can we take some advantage of this information that has been given to us? Like it is either in increasing order or decreasing order, anyways we take. So can we take any advantage of that knowledge? Like it is a like good thing to know. Okay. So for example, you have been given, yeah, again I'm copying the same thing. Now say x500 and x1000. You have been given 1000 elements and you need to search for a capital X, and you all know that x1 will always be greater like smaller than equal to x2, and this condition holds up till x999 and x1000. So you can say like these are arranged in an increasing order. Now do we need to search the entire array like given this information? No, we need not to search. What we can do, we will just find the middle element, say x500 is the middle element, and then we will compare our x with this x500. Now there are three possibilities. So case one, x, okay, capital X is equal to x of mid. Then like we have found our element, no issues. Otherwise x like capital X is smaller than x of mid. Okay, and the third possibility is x is greater than x of mid. Okay, in this case we are very happy that we have found that like our x exists in the list. But in this case what we need, what we can do, we can be sure that if our x exists, then it will only exist in the range of 0 to mid minus 1. Like if it exists, it cannot exist in the range of mid plus 1 to whatever the size is of array is, or the list is. So why this? Because every element on the right side of the middle element will always be greater than or equal to middle element. And since x was smaller than middle element, we can say it will never exist in the right side. So we are interested in only searching for the left side. And similarly, in the case of this one, we will always be checking in the range of Okay, if yeah, we'll always be checking in the range of right side, that is mid plus 1 to whatever size of array list is. Okay, so by this logic, can we reduce the say observable size by 2, by the factor of 2 at every step? Yeah, like we can always reduce our like the interested size of list by 2. We will check for mid and we will discard half of the part, and in the next step we will check for the mid again and we will discard either of the half part. So every time we are reducing our size by 2, like by the factor of 2, not by minus 2, it is divide 2. Okay, so given a for n, how many number of operations do we need? It will be okay. I've got some message, just a minute. Okay. Okay. Yeah. So, yeah, I was telling that given an n, how many number of steps do we require to like completely shrink the list? It will be log base 2n. And where does log base 2 come? Uh, for example, n will be like firstly it will be n, then it will be reduced to n by 2, then it will be reduced to n by 4, and then n will be reduced to some 2 power x. Okay, and if we equate this to 1, like we are left with only one element. So if we like equate this to 1, it will come 2 power x equal to n. And when we take log on both sides, so it will come nothing but log base 2n. Okay, that's why we can say like we only need these many operations to like reduce our list size to 1, and that one element we can obviously check with x if it is equal or not. So we can say that like earlier our time complexity, let's talk in the terms of time complexity only. Earlier the time complexity was order of n. This order, like if you are new to this thing, I would say this is like in technical terms, there are some big definition, but I will generally say that it indicates number of operations required. So earlier we need n number of operations to process a n sized input. Now we need only like log n plus 1 operation. So log base 2 n plus 1 operation. So you might be thinking like this is not a very big improvement, but yeah, it is, because let's say again n equal to 10 power 9. So you will need 10 power 9 operations. So 10 power 9 operations means on a 1 gigahertz processor, 1 second is required. But now you are just needing log 2 n plus 1 operation. So what is log 2 n? Like log 2 of 10 power 9 is approximately equal to 30, and 30 plus 1. So you need 31 operations, not 31 seconds. Okay, and how much time do it require to do 31 operations? It is close to 1 microsecond. So in 1 microsecond, you can do the same thing you were doing in 1 second. So it is like in 1 second, like even though due to memory constraint it is not possible, but in theoretical terms, we can say that in 1 second you are doing the same, like you can repeat the same operation 10 to the power 6 times. That is 10 lakh times. You are basically you can do 10 lakh times more work than you were doing in like by following the brute force approach. Okay, what is brute force? The brute force is nothing but a very simple approach that can be implemented without considering the time complexity. Okay, so you can do 10 lakh times more work just by optimizing some things, like by taking the advantage of information given to you beforehand. So is it not like a very good thing to do? So that will makes what? That will make our processors very not processors, like the processes executing on that processor is very fast, very fast. For example, when you say when you press some like button on say Twitter or anything, if it take 10 seconds to reflect, will you be interested in liking? No. But it takes only one, say, a fraction of second to reflect whether you liked it or not. Then you seems to be happy. Yeah, I liked it, and instantly the like number has been increased, and the symbol has become red or whatever color it is. So, like by this, I come to the conclusion of this session. And in this session, we have discussed what are algorithms and two examples showing the importance of those algorithms. So we can say that the session was quite interesting, and we learned the importance of algorithms in terms of time complexity, where we can reduce the time taken by any algorithm by by a factor of too large number. You can say that, like here we are reducing n to log n, and there were in we are reducing n to square root of n. So both are very big improvements, at least in the computational terms. Okay, so by this I will end my session. Let me know if there are any doubts or so.
Thank you so much, Paras, for giving your time.
Thank you, sir.